Okay, so thank you for the introduction. Yeah, so my presentation is about congestion control for vehicle safety communications. And I'm not sure if all of you are familiar with safety communications, so I've prepared an introductory slide for that. So in vehicle safety communications, the idea is that every vehicle periodically broadcasts a status message containing its current position, speed, and heading. And so if another vehicle receives this information, they can build up a neighbor table, and then they know where their neighbors are located. And we commonly refer to this as cooperative awareness. And yeah, so if we know where our neighbors are, we can build on top of this knowledge some safety applications. So for example, forward collision warning, which would issue a warning if we drive too close to our next neighbor driving right in front of us. Or also lane change warning, which will warn us if we want to make a lane change which is not safe. And there are a couple of more safety applications as well, and the basic communication type is this periodic broadcast of these quite short safety messages. So in this example, it looks, the vehicle density is not so high, but typically it's assumed that these vehicles send out such broadcast messages at a rate of 10 Hertz, so they send out 10 times per second. And if they all do this, and we have a lot of vehicles, the question is, how can we ensure scalability? And this topic becomes even more interesting with very recent results, because chip manufacturers such as Qualcomm are now considering to put this Wi-Fi technology, this is a special Wi-Fi technology called IEEE 802.11p, which has been adapted for these vehicular communications, and they are considering putting this technology in every smartphone. So all of the Wi-Fi chips are going to be equipped with this technology, so theoretically all pedestrians, bicyclists, and everyone could be participating in such safety communications. And we are already facing challenges with only fitting all the vehicles on the channel. So in the future this is going to be also a hot topic. This should really become reality. So congestion control for VSC is different from normal congestion control, which you know from the internet. So yeah, why not simply use TCP and we're done? But we have a different type of communication here. So first of all, of course, we want to prevent an oversaturation of the channel, which is basically congestion control. But the objective of the communication is to establish this cooperative awareness. So we have to make sure that vehicles receive enough messages to establish this cooperative awareness. And I'm going to refer to this term, or to this concept, as awareness control in the following. So we would like to have both and balance these objectives. The vehicular environment has some special challenges. So first of all, we are in an ad hoc network, so there's no central coordination which could tell us how many vehicles are there or which parameters we should be using. Second, we have a broadcast environment, and we don't have any message acknowledgements, so we can't know if our neighbor has actually got the latest position update that we sent out. And finally, vehicles are moving a lot, obviously, so the vehicle density is changing all the time, and this change in their position does not only influence channel load, but it also influences what the requirements are for the cooperative awareness. So, and we have to balance all of this in a real-time adaptation. So, a couple of questions arise here when you would like to design a protocol for congestion control in these vehicle safety communications. So first of all, what are the basic principles we should be sticking to? What are the requirements? Then what would be the optimal outcome? Like if we had all the knowledge in the world and we could do whatever we wanted, what would be the ideal outcome that we are targeting to get to? And then next question is, which control strategy could get us there? Like which parameters should we be tuning and how? in order to get to this outcome. Yeah, and finally, what could a protocol look like which uses this control strategy and tries to get to this optimal outcome? So this work is structured as follows. We first start with setting up some design principles. They are derived on the one hand from the characteristics of vehicle safety communications on the one hand. So there is these two aspects of congestion control and awareness control, and also from the related work. So there has been a lot of related work on this topic already, and but they are all try to optimize different things and have different metrics for evaluation. But I'm going to come to that in a second. So on top of these design principles, we created design methodology. So first we look at which control dimensions do we want to adapt. Then what would be our optimal outcome? Optimal in quotation marks, because it depends of course on how you define it. Then what would be a control strategy to get to these optimal points? And finally we also look at fairness. And on top of that we build a protocol, which I'm going to present to you in the last part of this talk. The work presented here is taken from two publications. So the first one was presented at IEEE Networking, Vehicular Networking Conference in 2011, where it received the Best Paper Award. And the second publication is currently under review, so you're going to get a sort of sneak preview. Okay, so let's get started. On the left side here you can see some exemplary related work. And we would now like to derive some design principles for congestion control. So the first principle is very obvious. Since we're an ad hoc network, we would like to have a decentralized control. Then in the related work, many of them talk about fairness, but they all have different, they all address different aspects of fairness. So we identified three different aspects here. So the first one is participation rule, which means that if I contribute to congestion in one location, I should be participating in congestion control. This is fair, right? And this also means that we have to exchange channel information, but we will get back to that later. The second aspect is local fairness. By local fairness, we mean that if vehicles are located physically close to each other, they share the same channel, so they should also be regulated in a similar way. And finally, global fairness, which is a bit more difficult to explain. What we mean by this is we try to approximate max-min fairness. So we try to maximize the minimum allocation. The idea is here that unlike in another network, where it could be okay to throttle some individual nodes for the greater good, so that all the others can transmit more, in safety communications, this doesn't make sense, because if we throttle individual nodes, these nodes can become safety risks for us. So if a vehicle is not able to send out its broadcast messages and tell the others where it is located, it could become, the others might not be aware that it's even there, this vehicle, so it could become dangerous. Yeah, and the last aspect is this cooperative awareness, which is also addressed by quite a few publications. And for us in congestion control, it means that we should defer to what safety applications tell us. So we should make the adjustments within the limits provided by the safety applications. And our objective here is to find a solution which addresses all of these 5 design principles. Okay, now let's look at which knobs we could potentially turn in order to do congestion control. So these are all suggestions you can find in the related work. So obviously we could tune our channel input. That we could do with transmit power control, transmit rate control, and when I talk about transmission rate, I always mean how often are packets generated, so I don't mean data rate. Of of course, we could also tune data rate and message size. But the problem is that, okay, for data rate, different studies have shown that there's, for current hardware, there's actually one data rate which is optimal, so it doesn't make much sense to tune this parameter. And for message size, we are also subject to standardization, so we can just send out packets like we want.
So when you say data rate, the transmission rate?
Yeah. So this one here means how often are packets generated, these broadcast messages, and this is, for example, a BPSK or PPSK, the modulation speed. That's what I mean.
And there's one rate that's optimal?
Yeah.
Are you going to talk about that later?
No. So this has been shown in different studies, in field tests as well as in simulation studies. So, but I can refer you to the.
Like roughly, what are they when they optimize that? Are they balancing coverage versus power? What are they?
They optimize reception performance. So
lower is better, right?
Yeah, 6 megabit per second is actually what they have identified as optimal.
So okay, so somehow 6 is the best because that's the lowest one and there's nothing lower.
Oh, there's something lower. So we could also use BPSK, which would then be 3 megabit per second.
So why is that worse than 6? I guess it's outside of your area. Maybe I'll ask you offline.
Yeah, maybe we can discuss it later.
But so there's a fixed. We're going to think about just using 6 megabit.
Yeah. So I mean, it could also be that in the future, with different hardware, it becomes an option again to tune this parameter. But right now, if we want to change the input to the channel, these are basically our options. And okay, there are also other works which address tuning CSMA parameters. So we could play with contention window size or with CCA threshold. But we consider these to be more helpful for message prioritization, to give faster channel access to message types which have higher priority. There are also other ideas like STDMA overlay networks, but in this work we're going to focus on these two parameters which are also typically used for congestion control. So yeah, let's look at what our optimization objective actually is. So we want to establish cooperative awareness, and to do so we have to understand what is cooperative awareness. So we actually have a spatial aspect and a temporal aspect. Spatially, so let's consider these vehicles here. So we have a traffic jam on this side and we have sparse traffic on this side of the highway. And so these vehicles are driving slowly, this vehicle is really fast. And but they are all sharing the same channel, so they are very closely located together. So this vehicle here, for this vehicle it would be sufficient to communicate to a shorter range than this one. Because if we, because for this vehicle, for example, this one could be a potential danger, so it is necessary to communicate to a greater distance. The actual distance you have to communicate to depends on your driving context, especially on the relative speed to other vehicles. On the other hand, from a temporal aspect, we look at packed into reception time. So this means for a particular neighbor, how often do I get updates from this neighbor? This is what we are interested in, because if we get updates from a neighbor, we can update our estimation of his position. Yeah, okay. So we have these two aspects, and if we look back at our parameters that we could be tuning, so this one we can obviously address with transmit power control. And this one here is a bit more complicated because obviously it depends on your message generation rate. So if you send out every 500 milliseconds one packet, for example, then your packet into reception time can be lower than 500 milliseconds. And but it also depends on your transmission power. And here we would like to find a balance. Like we would like to find out what would be the optimal setup of these two parameters to optimize reception at a certain distance. So let's look back at our objectives again. So we would like to have both congestion control and awareness control. And we have basically three options. So we could do transmit power control. So we use a fixed transmission rate for everyone. And then we adapt power. Or we could use a fixed power and adapt transmission rate. Or we could do a joint optimization of both dimensions. But then the question arises, which dimension should depend on what? So what we're going to look at in the following is first, which parameter combinations of transmission rate and power optimize reception performance at a certain distance. And second, which control strategy can get us there. So the setup we use here is very simple. So we have a very, very long road with equidistant vehicles, and it's pseudo-circular, so the last vehicle thinks that the first is his neighbor. So it's an extremely long circle. And we have three different vehicle densities, and we use a wide range of transmission parameters. So a transmission rate of 1 to 20 Hertz and transmit power of 0 to 30 dBm. And what we are going to look at is what is the average packet interception time at each sender-receiver distance. And we use this kind of simple setup now to focus on, to exclude certain side effects of movement and just to focus on the pure propagation. So here are some results. What we see in these plots is here transmission power, transmission rate, and what is the average interception time at a particular distance. The distance is given here, and we also have different vehicle densities. So here we have 50 vehicles per kilometer, and here we have 100 vehicles per kilometer. And on the bottom here, this is kind of a heat map of this graph. And the arrows, they point to the minimum. So we would like to know which combination of rate and power gives us the minimum average packet interception time. And we can see that for each distance and vehicle density, we get to a different point. And so the question is there a pattern behind this?
So how is this the average calculated for the IRT? Well, in the sense that not everybody hears everybody, right? Like, you drew those pictures of the coverage area, like some people will transmit and will just be maybe heard locally, like by a small group.
Okay.
Not.
They are just, they are all using the same transmit power set, the same parameter setup. We have a homogeneous setup, so all vehicles use the same transmit power and transmit rate. And this graph shows for a distance between vehicles, and okay, it's basically an average over all neighbors at a certain distance. But it is calculated for each sender and receiver pair.
Yeah, that's pretty, so okay. Am I the only one who's confused here?
Yes.
So I am.
So I guess your question is, what do you do with cars that don't receive at all, right?
Yeah, like how do they get calculated? So for instance, like
I guess at 100 meters, in your simulation model, are there any cars at 100 meters that don't get any packets?
Yeah, of course, they don't get every packet, so you have a
don't
reception.
Get, not every, it's clear, but don't get any packet.
Any packet at all.
0 packets.
No.
I guess it doesn't happen. How about 300 meters? Do you have any node pairs with a separation of 300 meters where you don't get any packets?
I don't see why that should be the case.
So how big is your circular highway again?
It depends on your transmit power. So I've set it to 3 times the carrier sense range. So in order not to create a transmission around the circle, so to say, and not across. So in order to exclude unwanted effects.
So what about, can you go 1,000 meters on the circle? Like at 1,000 meters, are there are nodes, they don't have any, there are no packets received at 1,000 meters?
I guess it could happen theoretically. I mean, at each distance you have a certain packet reception probability.
So maybe.
So if you have really bad luck and all the time, I mean, it might take a while until you receive a packet. If the simulation time wasn't long enough, then it could happen. But this average here can also be very simply calculated from from the probability of packet reception.
So like, let's just take one of those boxes again. So we take the box through like the upper right. So there's 50 nodes per kilometer on the road, right? And then you look at all the pairs at some instance, and the cars keep moving around. You look at all.
No, they're not moving. That's it.
So you just take one snapshot of the cars, and you look at all the cars that are pairs that are 300 meters apart, and you run a simulation for a long time or an analysis, right? And you see, for that pair, like packets were received, and you calculate the IRT for that pair, the average, and then you average that over all pairs at 300 meters, or is there some bin around like 290 to 300, or?
No, since they are equidistant, I can use the exact distances, so I don't have to use bins.
Okay.
That's also why I use this simple setup to exclude such effects.
And does CSMA and all those effects come into the picture?
You mean if CSMA is simulated here?
Yeah.
Yeah, so this uses the network simulator too, and it has quite a sophisticated model of 802.11 megainfo. But these plots here can also be really simply calculated. So your average packet interception time is actually your transmission interval divided by your reception probability. So it's a geometric distribution, and from this it follows.
So you kind of assume that somehow that because the rate at which they send is kind of 10 hertz is pretty low in terms of packets taking milliseconds, right? That by the time the next time you go to transmit, whether you succeed or not is independent of the past.
Yeah,
right?
that is the basic assumption. That's true.
Yeah. So do you essentially use that success probability? So you could generate graphs like this using the success probability calculation, or you could run NS2 and have it simulate for a really long time.
Yeah.
And you've done both and you get the same thing?
So I haven't calculated the probability of reception, but I have extracted it from the simulation. And if you do the cross-check and you divide your transmit interval by your probability of reception, you get exactly the same graph.
And so somehow, like looking at these graphs, right, you would think that kind of, I mean, it's hard to tell, but it looks like kind of the optimal transmit power and rate is fairly similar in all 4 instances. Is that the right interpretation? Like what you want to do for any one of those groups, right, is like for the people at 300 meters, you'd like to choose everyone a transmit power and rate at the bottom of the bowl.
Yeah.
And then, but maybe it's a different, the position is a different transmit power and rate for.
Or these little black lines point to the optimal point.
Okay, yeah. So are you going to talk about those now? Is that what
Yes.
Yeah, thank you. Yeah.
Okay. So we have seen these graphs now, and so for example, for 50 nodes per kilometer and a distance of 300 meters, we identify that the lowest average packet interception time is at 24 dBm and 11 Hz. So we have done the same procedure for many different distances and for all vehicle densities, and the result is plotted here. So in this plot, you can see the transmission rate, and here the transmission power. So I have plotted it in different diagrams so you can see the trend better. So this 24 dBm can be found here, and these 11 Hz can be found here. And we can see here 3 different vehicle densities. So the blue one is 200 nodes per kilometer, green is 100, and red is 50. And what we can see here is that for transmission rate, we get a different result for each distance depending on how many vehicles are there. While for transmission power, we get almost the same transmission power, which optimizes average packet interception time for a distance. There are some outliers here, which I could also explain if you are interested. So, yeah, what we can learn from this is that the optimal power actually does not depend on how many vehicles are there. And this is for us quite convenient because it makes things a lot easier. So,
Could you just show us, is it clear to everyone why that's true?
The curves kind of coincide. Conclusion is like that. So the curves are for different densities and they are all the same with the lower graph.
If there are more nodes, there should be more interference in some ways. So then I might have guessed that lowering the transmit power is better, but then you also reduce your reception range maybe.
So actually what this plot here shows you is that for each distance there's one power which gives us such, or which corresponds to one of those lowest points. And the power does not depend on how many vehicles are there. So if you look at it from a different perspective, so if you want to get to a certain distance, if you use a too low power, then you can't get there because your probability of reception is too low. But on the other hand, if you increase your power, then you are creating a lot more interference. And since everyone is doing this, then you can send so much more packets, so this decreases your packet generation rate. So your packet interception time also goes down.
So your optimal power is always just a little more than the maximum range that you want to achieve.
Yeah.
Just
Well,
enough
actually,
power
the exact value here also depends a bit on which metric you use. So I've evaluated different statistics for the packet interception time. I've also evaluated different percentiles. So because in the geometric distribution, the average does not correspond to the median. That's why I've also evaluated different percentiles, and you get the same trend. So the absolute values for power are about 2 dB higher if you use, for example, the 90th percentile as a metric. But the trend is the same, so there's still one power for each distance which optimizes your packet interception time.
Is there anything in the simulation which is vehicular specific, as in with the same placement of nodes?
Yeah.
We could have interpreted it as like some fixed AP and client
Right,
ad
this
hoc.
is not vehicle specific, right?
Right.
That's true. Yeah.
But it's broadcast.
Right, every packet is
Yeah.
No TCP.
So somehow it just seems to say, oh, the product of the density and the transmission rate, the message rate should be roughly a constant.
Right. So actually this is the principle of communication density here. So it doesn't matter, so if you use the same power, then it doesn't matter if you have 100 vehicles which send at 1 Hertz or if you have 50 vehicles which send at 2 Hertz. So for the channel it's the same input.
Yeah.
Unless you change the vehicle density. Right. So it, that's also why this ratio here is about 1 to 2 to 4.
Yeah, right. Yeah.
Yeah. So I didn't put all this in the presentation because it would probably get too long. Yeah, but okay. All right. So
but somehow, right? If 2 for 200 nodes per kilometer is good enough, right?
Mm-hmm.
And it's also good enough for 100 nodes per kilometer.
Mm-hmm. This doesn't say it's good enough. It means what is the lowest you can get. So what is good enough depends on your driving context. So this is just what is the lowest you could get at all.
Right. So okay, I guess we're going to talk now about what's good enough in relation to what you can get.
Yeah, I hope I answered your question.
Yeah, I understand. You yeah.
Okay, so from this result that for each distance there's a power which actually optimizes our reception performance, we have devised a joint rate power control strategy. So it first starts with, okay, we also assume that we have a minimum and a maximum transmission rate. This could be, for example, 1 Hertz and 10 Hertz or whatever. Or this could also be set individually per vehicle, which I will also come back to later. And so we start with setting our transmission rate to the minimum and setting our power to the optimally for the desired distance. And then we evaluate our channel load. So so very simply, if our load is now below the target, so we have also a target channel load, which we express in channel busy ratio. That is how the ratio of the time the channel was busy and the evaluated time. So if we are below the target, then we would want to increase our rate. If we are above the target, then we would like to decrease our rate, very simply. But what do we do if we are now already at our minimum rate and our channel load is still too high? In this case, we would want to decrease our transmit power so that we can still get the minimum packet interception time that we need, and but we can't communicate to the distance where we actually want, but we can still talk to our closest neighbors. So if we do this and we play with power, then we additionally have to change something here. So if load is now below our target, we first check if our power is currently at the optimum. And if it is not, then we increase our power first. And if power is already at our optimum, then we would increase our rate. Is that understandable?
You mind repeating that? I kind of got lost there.
Okay. So you start, actually, let's look at an example. Okay?
Just the power, okay.
Maybe this is easier. So this is now these 3D plots we saw before. This is the same thing seen from top. So we now just look at the map. And you can see transmit rate here, transmit power here, and the colors now indicate packet interception time, the average packet interception time. And on this side here, we see the corresponding channel busy ratio, so the fraction of time the channel was perceived as busy. So what we would do is, let's say our minimum required rate is 2 Hertz. And also our channel load target is 90%. So we would start at 2 Hertz and we would set our optimal power, which in this case is 24 dBm. And then we would increase our transmission rate until we are at our channel load target. And you can see for channel load what happens here. And what I haven't mentioned before is that this optimal power also depends on what your channel load target is. So if you, for example, don't want to go to 90% but you want to go to 70%, then you don't need the same transmit power to optimize reception because you have less interference, so a smaller transmit power optimizes your reception already. So it's actually a function of what your distance and your channel load target is. That's your transmit power. And so the same strategy here for 100 nodes per kilometer. We also start at 2 Hertz and we pick our transmit power of 24 dBm, which we identified previously as optimum, and then we increase our power, our rate until we are at the channel load target.
So, excuse me, how do you adjust now this optimal? So I assume your optimal transmit power is from the previous slide, where you look at the density, given density of nodes. And then how do you adjust for the CVR, this maximum, this optimal transmit power? You said it not only depends on the...
Yeah, so what we basically need is something like a lookup table, or maybe you can also find a function that calculates it, which tells you for... Okay, so the channel load target should be the same for all vehicles, because if one vehicle tries to optimize for 50%, the other for 90%, then it's not really going to work. But, so if you know your channel load target, and then you can derive your, you can sort of create a lookup table for your power. Okay.
So the power depends on the distance that you want to achieve. Right?
Yeah, and on your channel load target. On both. So if you want to get to a lower channel load target, then a lower transmit power is sufficient to optimize reception performance.
So this channel load target, is this important when you introduce new applications where someone is actually extremely important, or you have priority users? So what would be the reason that you'd like a different channel busy ratios threshold?
Yeah, so one option would be, for example, you want to restrict channel access time. So if you evaluate what your channel access time is, in my results it was on average, at 90% CBR it was like 7 milliseconds on average, but it is a heavy tail distribution, so you could get longer channel access time. So this could be a reason to restrict it. Or what is also commonly seen as an option is to save some bandwidth for emergency messages. So in vehicle communications we have two message types. We have these broadcast messages, and we also have event-driven messages, which are sent out if something happens. For example, I drive over an icy road and my car starts to break out, and then my car will send out an emergency message. And so it could be desirable to save some bandwidth for this purpose. But for our work, it doesn't really matter where you want to set it. So in my results, the optimal reception performance was actually near 90% CBR. But yeah.
Okay. How do you currently define your goal for optimality? So you want to minimize the packet in the reception time at a certain distance?
Yeah.
Or the average overall distances?
No, so we look at what is your target distance, and within target distance your reception performance will be equally good or better, because your probability of reception will be at least as good or higher, unless you have some strange propagation effects. But if you assume that the probability of reception degrades more or less gracefully with distance, then your reception performance within this distance will be better.
So it's minimize packet interception time at the target distance.
Yeah. So, and you can't optimize for all distances simultaneously.
What is the motivation for introducing power control? Is it that the target distance might change, or is it that the propagation environment might change?
Yeah, both. I mean, if you know that you are entering, for example, a non-line of sight environment, then it could make sense to apply a different setting, because then your probability of reception will be different.
Okay, so based on your previous results, you want to adjust your power so that you can just about reach this target distance? Just a high level, just a little more than the target distance, right?
Yeah.
And so now you drive on and the propagation environment changes. Then you may need to adjust power to reflect that.
Right.
The power is set again to this target distance.
Yeah.
I guess the question is now, how do you get this feedback of whether you're reaching the target distance in your algorithm?
If you reach it?
Yeah. How do you know that the nodes at the target distance are getting the messages?
Well, it's difficult since we don't get any acknowledgements, so we can't know for sure if they have received it. But if we have a reasonable assumption of what the probability of packet reception is at this distance, then we can infer the probability that the car has received the packet.
Where do you know that from?
Well, that's an inherent problem of this entire communication, because I don't get any feedback. So
you want to come up with a solution that where you do not get any feedback from the receivers.
Yeah. So
and then you say the only thing you have is that you can monitor how busy the channel is.
Yeah. And also the channel busy ratio actually has a very nice property.
The what?
The channel busy ratio, the fraction of time the channel was busy. It has a very nice property that we talked previously about communication density. So the product of number of nodes and transmission rate and transmission range. And actually there's a linear relationship between these two things. So if we measure our channel busy ratio, it tells us implicitly the communication density. Up to a certain point, like beyond 90% CBR, then the channel becomes so unstable that the feedback doesn't work anymore. But up to about 90%, it is a injective relationship.
So you're saying that channel busy ratio is some indirect feedback about the range that you're achieving?
No, not about range, but about how many nodes are there.
Congestion.
Does that have to do with range times density?
Yeah, that's how the communication density is defined. So this was in a paper from Daniel Zhang in 2007, and he showed that in a stable environment you get the same propagation characteristics if you have, for example, 100 nodes per kilometer with 1 Hertz or 50 nodes per kilometer with 2 Hertz, if they use the same power. And he introduced this metric of communication density, which is your product of transmission rate, vehicle density, and transmission range. That's how he defined it.
So as compared to the vehicles being static at some point of time when you're measuring, and compared with when you're moving, would this channel busy ratio change, or is it independent of that?
I'm not sure if I understand your question. So you're asking if the vehicles are moving, if this channel busy ratio changes? Yeah, of course it's going to change, because your vehicle
density. Would that
density
change your optimality, the criterion that you choose for what power that you choose for the minimum packet reception time? Would that change?
The power?
The power that
No.
you choose.
So we saw before that this optimal power is actually independent of how many vehicles are there. And that's what makes things easier for us. So we can infer how many vehicles are there, and from the channel load, from the CBR.
So this power inference is clearly, it's just related to the maximum target distance that you can reach. If I choose a lesser power, say half of it, I'm going to reach half my target distance. Is that the correct understanding?
So you mean if you have your power, then you also have your target distance? I'm not
what
sure
I'm trying to
understand
understand is how the power control is reflecting what the characteristics of the channel, or how you're helping or your system.
How the power control?
So by controlling power, how are you helping your system?
How am I helping the system? Okay, so if I mean, it could be an alternative to just assign the same power to everyone. But in this case, I would assign a higher power also to vehicles, for example, those which are stuck in a traffic jam. And for them, they don't have the requirement to transmit so far. So I can save a lot of channel if these vehicles send at a lower power. That's the basic idea. Okay, so in the joint control strategy we have seen that we primarily focus on rate control, because the power control is more or less simple because we can use a lookup table concept for this. And so for rate control, the question is what would be fair here? So remember, we also want to do awareness control. So our metric is what is our safety benefit. This could be different metrics, for example, the tracking accuracy of the vehicles. So if we have transmission rate here and we don't expect that there's going to be an infinite gain of safety benefit by infinitely increasing transmission rate. But we expect more or less such a curve so that there's going to be a saturation. And if we look at safety benefit, there's going to be something where you say, okay, below this value we can't function anymore, our safety application won't work. And similarly, we could derive a maximum value, which says, okay, my tracking accuracy is now at 10 centimeters or whatever, I don't need to be more, I just need to have a higher update than that. So if we now look at the crossing of these lines, we can infer a minimum and maximum transmission rate. If a vehicle is in a different driving context, so for example this red one could be one which is stuck in a traffic jam, so it doesn't move much and it doesn't have to update so frequently. We can actually, so what we do here is each vehicle can have its own minimum and maximum transmission rate. And what we want to do is we want to adjust within this limit. And we consider it to be fair if vehicles would get the same safety benefit. So, but this could mean actually a very different transmission rate for the different vehicles. Okay, so this was now the methodology part. The protocol itself now expects three things as an input from safety applications. So first of all, we need to know how far we want to get. We need to know what is our minimum and maximum transmission rate. And we've just seen that those could also be set individually for vehicles. And the protocol that we developed is called Pulsar. And the basic idea is very simple. So we want to adjust between our minimum and maximum rate. And to do so, we periodically check our channel. So we check what is our channel state, and are we currently congested or are we not congested. And the channel load assessment consists of two parts. First, our local channel measurement, and then also an exchange of channel information between vehicles. And also, as we've discussed it before, we adapt the transmit power based on whether the target distance changes or based on the channel load if we are already below or at our minimum rate. Excuse me 1 second.
So that's not through feedback, right? So there is no feedback in your system.
Sorry?
Local channel measurement.
Yeah.
When you say channel measurement, are you
Channel busy ratio.
You're sending a periodic burst of packets and measuring the channel quality as a receiver?
No.
Piggybacking?
No, so the Wi-Fi device actually can give us the channel busy ratio already. So it always monitors the received signal strength, and it checks if this was above a carrier sense threshold or not. So you have this carrier sense threshold, and if your noise level is above this threshold, then the channel is perceived as busy, and otherwise it's perceived as idle. And so this channel busy ratio measures the fraction of time that you perceive the channel as busy. And this we can get this already from the Wi-Fi devices. So while the basic idea is really simple, we also introduce a couple of mechanisms in order to meet our design principles, which we addressed in the beginning. So when we or the basic functionality is this. So this is time, and at certain points in time, we monitor the channel over a certain period, for example 200 milliseconds. Then we calculate or we get our channel busy ratio from the radio, and then we take a decision based on that. And since we are using AIMD, we have also a synchronization between nodes when they take the adaptation. This is based on GPS. So, but if we now use our channel busy ratio and we monitor it for only 200 milliseconds, we are going to have measurement noise. So, and this could trigger us to take wrong decisions. So we additionally introduce a mechanism which we call self-averaging. So it's basically a digital low-pass filter. And so it's really simple. So we take the old value, and we take half of the old value, and we add 50% of the new value. So this parameter could also be tuned as well. But this one here, so the idea is to reduce noise of our measurement. Okay, so if we now base our decision only on our local channel measurement, as we have discussed it so far, what could happen is the following. So this vehicle here measures congestion at the channel, while this vehicle here doesn't. So it could happen that this one has more neighbors influencing it. So this one has a congested channel, but this one not yet. But on these lines here, the solid line is your reception distance, and this is your interference or carrier sense distance. This is now very schematically drawn as a circle. In reality, it's not such a sharp line, of course, but this is for illustration purposes. So, if we now only base our adaptation on our local measurement, what could happen is the following. So this car here measures congestion in the channel, so it's going to decrease its transmission rate. Then it's also going to decrease the interference at this car. So this car thinks, oh great, the channel is free, I can increase my rate again. And then this car is going to measure more congestion, and it's going to go down again, and this car is going to go up. So we run into an effect which we don't want, because this car gets pushed down all the way. And if you remember that we talked about global fairness, this is actually a violation of this concept. The same thing could happen if we have different transmit powers. So this car uses a higher power than this one. So this one also doesn't have a chance to tell this one that it is congested. Yeah, so when you look back at our three fairness principles, the first thing, participation. So we've already talked about this, right? So this car here should actually be participating in congestion control. The local fairness is also kind of intuitive, so you don't want to have one neighbor standing at 1 Hertz and one at 10 Hertz if they have the same safety requirement. And the third thing, the global fairness, is illustrated here. So what we can see here is a crossing. So the black line here is supposed to be the road. And on the y-axis you can see the transmission rate allocation. And so one allocation here pushes the node in the middle to the lowest value, while the other one reduces rate to a further distance, but then the ones in the middle can transmit at a higher rate. So our objective is to reach something like the blue one, because if we do this, so this plot also assumes that they all have the same communication demand. So then we would push this one down to the bottom, and it may not be safe anymore. So in order to now achieve this fairness, we introduce an information sharing mechanism. So remember, this car here was congested and this one here wasn't. But this one is contributing to this congestion. So what we could do is, this one could just increase its power, but that would not make things better for the congestion. So, but if you have a congested channel, we have a lot of vehicles in the area, so we can use them. So let's say there's a car here in the middle. We could use this car to tell this one that here we have congestion. And the scheme we have developed is actually, it's actually simple. So in our packets, in our broadcast packets, we piggyback two things. So first, we have our local channel perception, and then also the maximum CBR we received from a neighbor within a certain distance and within a certain time frame also. So if we know this, so if this car here sends out, I have heard someone who has a congested channel within my range of whatever 200 meters, that should be defined of course, then this car here can calculate the distance to this one as well as the additional distance and know that there is someone within his interference range who is congested, and then he can take this into account when reacting. However, we also have to take into account that if we introduce this kind of information sharing, we have a dissemination delay. So we don't have, while we can measure our own channel load instantaneously, it takes some time to get the information from our more distant neighbors. So that's why we do the following. So we monitor the channel in this interval, and we receive information from our neighbors in this interval, and then we take our decision here. And this can also be shifted in this direction. The actual rate adaptation uses AIMD, so we also get some sawtooth-like curves like TCP. So we have an additive increase and a multiplicative decrease. And in addition, we do the following. So we also have a target rate, which is basically a neighbor average. It looks at what is the neighbor's transmission rate and calculates such an average. And the idea is the following. So the strict max-min fairness would lead to a very sharp cutoff here. So, the scenario we see here is this crossing that we saw before, but only looking at one road. So here in the middle is actually the other street, but it's not plotted. So at this point we have the highest congestion level, and if we don't take into account the transmission rate of our neighbors, we get quite sharp cutoffs here, which does not make much sense in terms of local fairness. So we would rather like to have a result which is more smooth like this. And also, if we take into account the transmission rate of our neighbors, we also achieve a faster convergence if vehicles are moving. I will show you an example in just a second. The final mechanism I would like to mention is message rescheduling. So we know this already. We monitor our channel, we receive channel information, we take a decision. And let's say our decision was that we want to go down, and we get a new transmission interval. So in this case, and this graph here is when we transmit our packets. So this is how we monitor our channel, and this is when we transmit our packets. So let's say we transmit our last packet here, and this is was our transmission interval. So our next transmission will take place here. Now, if we get this result that we have a new interval, we could now just wait until we have sent the next transmission and then use the new rate. But then our adaptation wouldn't take effect immediately, which is not what we want. And this also leads to very unstable behavior, which has been also seen in the field test. So instead, what we do is we check, since our, so we are now here at this point in time and we take a decision, we check how much of our interval has already passed. So let's say 25% has passed. And then what we do is we take the new interval and we take 75% of it, because we have already covered 25%, and we reschedule our transmission to this point. Okay, we have now actually covered everything, so I'd like to show you an example of what the performance looks like. So in this video you're gonna see 4 plots moving simultaneously. So here we have the transmission rate, here we have the channel busy ratio, here we have the vehicle position, which is a bit distorted. So you can see here are 5 meters and here are 500 meters, but if you plot differently, they are just on one line. So, and here you can see the vehicle density for each X position. And what we're going to see now is 2 groups of vehicles approaching each other and passing each other. And the vehicle density is changing very much in this scenario, because first the vehicle density is so low that they can all use their maximum rate allocation, but then when they cross each other, the channel is congested, so they have to reduce it, and then when they separate again, they can go up again.
So is that the mechanism where you adjust your transmit power based on CVR?
No, in this case we don't adjust power at all. In this case we assume that they all have the same target distance, because otherwise it's more difficult to see the train. But what we can see is that they are now approaching each other, and we are always going a little bit up and down, which is this AIMD mechanism, and that's also why the protocol is called Pulsar. And we can see that the channel load actually converges to our target, which was set to 60% in this case. And now vehicles are separating again, and we can see that they are going here up again. And also, what is not shown here, but is that if we don't include the target rate mechanism, so we take into account the transmission rate of the others, then we wouldn't get such a smooth curve here, but we would get kind of an X-like shape, because they don't converge fast enough. Okay, yeah, so to conclude, what have we looked at here? So we have started with design principles, which we derived from the characteristics of the vehicle safety communications. We looked at a design methodology consisting of control dimensions. We looked at what would be the ideal outcome if we could control everything as we wanted to. Then we looked at what could be a control strategy, and also at fairness. And finally, we translated these principles into actual protocol mechanisms. And so for decentralization, of course, we have distributed algorithm. The participation rule is addressed by two-hop piggybacking. Local fairness is addressed by the target rate mechanism. Global fairness is addressed by a couple of mechanisms, actually. And the deference to safety applications is addressed by the target distance and minimum maximum rate concept. Okay, that's it. Thank you for your attention.
Thank you.